All right, so this week we're going to take a look at a very short unit on what we call parametric and polar equations. You might have seen the words on the graphing calculator when you press mode, function, parametric and polar. We've never talked about these other two modes, parametric and polar, but we're gonna start using them a little bit today. Okay, parametric we'll focus on today, and polar probably Tuesday, Wednesday. So when we graph things on the graphing calculator, we can only graph things easily that basically pass what test? Vertical line test, which tells us that what we're graphing is a what? Yep, a function. Okay, so when you're graphing things in y equals mx plus b, you can get lines, or you can do like a quadratic. So you can do parabolas. We can get different shapes. But something that's kind of hard to draw would be a circle. Because a circle fails the vertical line test, it's not a function. So there are different modes we can use. And we can graph things that fail the vertical line test, but we can graph them pretty easily. Right, so I'm just going to show you a few examples of things. Some of these, I don't know the equation to do that. It could be a pretty complicated equation. But some simple ones we can do are like spirals, circles. That's a simpler one on the end than the other two. And we'll look at how you could do that one. Might have something to do with a sine wave. I can't remember. Right, basically, different kinds of graphs that we haven't seen before. So let me start to try to explain what parametric functions are. First of all, when you graph something in what's called the parametric system, you're not graphing. You can't just have one formula. You need two. So if you go to mode and keep it on function, you want to type something into y1, you just type in like 3x plus 5. You could hit graph. You'll get a picture. If you set it to parametric and you hit y equals, notice each graph now has two things. What basically parametric does is it breaks down your formula into one formula to calculate x's and a different formula to calculate the y's. That's what parametric is. So two formulas, one for x, one for y. So when I talk about two different functions here, I'm talking about one formula that's going to generate all the x values. Call that formula f. And we'll have a different formula. Call it anything you want, but I'm calling it g here. And g is going to generate the y's. In parametric, there's this idea of an interval. Okay, the interval is basically the numbers. It's like the domain. That's what it is. It's the domain. It's the numbers that you are plugging into your formula. Which formula? Both formulas. The formula for the x's and the formulas for the y. Now, when you take and you plug in all the different numbers that you can, let's say your interval goes from 0 to 10. That's your domain. You have to plug in every number from 0 to 10. And that, if you could do that and generate all the ordered pairs, that would be your graph.
Is the interval t with an underscore, with an underline, or an I?
The interval, that's I. Yeah, so we call the interval an I. Now, when you have to plot all your points, you literally have to plug in every single number from 0 to 10, like 0, 0.001, 0.0002. I mean, you have to plug in everything. Obviously, it's not possible. You can't plug in every single possible value from 0 to 10. So we do it just like we do any graph. We plot a few points, and then we connect them. The key is we're going to be doing things that curve. So when it curves, you might need a few more points than you normally would for just a line. And we're going to use the calculator to help us as well. So when you draw something parametrically, our book refers to it as a curve. Whether it's really curved or straight, they still call the picture a parametric curve. Right? So if you had a line that was drawn on the screen, they would call that a parametric curve. So we have to come up with two equations. Okay, let me show you, I'll come right back to this, but let me show you an example. That's an example of a parametric system. The formula for x is 1 minus 2t, and the formula for y is 2 minus t. In this particular problem, you are allowed to plug in anything between 0 and 1, including fractions and decimals. Why 0 to 1? I don't know. They usually just pick a minimum and a maximum for what you can plug in for t. Okay, and that's your domain. All right, let's go back here. So your two equations. Sometimes I call them like a system of parametric equations, because it's basically what it is. It's two equations. And the variable that you use parametrically is t. So if you notice in the graphing calculator, there's this button, and it says x, comma t, comma theta. Well, x is the variable when you press it and you're in function mode, you get an x. When you press this button and you're in parametric mode, you will get a t. Okay, so we got to get used to using a t on the calculator for the variable. Now, you can call it a parameter, you can call t a variable. I'm not really sure the technical difference between the two, but t is essentially your variable. And it's not hard to get used to using t because you still press the same button on the calculator. It's just when you press the button now, it gives you a t instead of an x. But you're still using the same button. If you only fill in one of the two equations, it won't draw anything. That's like only knowing your x value and me saying graph the point. Well, you can't. You need the x and you need the y. And this is a little different than the kind of graphing we're used to. So hopefully by now, most of you are pretty good at, if I gave you an equation, you would kind of know what it would look like. Like we know a square root, kind of looks like that, or a quadratic has a U shape to it. With parametric, we've never worked with them, so we kind of have to start at the beginning and kind of learn, okay, if this is that and this one is this, right, it's going to look like this. So we'll start to kind of learn some simple parametric equations, but we never really get into anything quite that complicated. Maybe like the one on the end, but the one in the middle, it's pretty complicated. Okay, so the two equations that you have, the one for x and the one for y, they're called parametric equations, and they give you what's called a parametrization of your curve. So if I give you a problem and I basically say to parameterize it, what I'm asking you to do is take something like this and turn it into parametric form. Okay, we can take any graph that we already have and we can change it to parametric. Or we can take something that's parametric and we can change it back to what we're used to, like y equals function notation. And that's part of what we're going to do. Okay, convert between the two formats. So two parametric equations give you a parametrization of your curve. Remember, curve doesn't necessarily have to mean it really curves. Anything drawn parametrically is a parametric curve, at least in our book. Curves can definitely intersect themselves. So you saw that on the group of first pictures I gave you. They can come back and cross over each other. Where when we do functions, that doesn't happen. Because if something crossed itself, it would fail the vertical line test. Okay, so how do you graph something parametrically? Well, because you have a domain, you have an interval for numbers that you're allowed to start at and stop at. That's what we're going to use to kind of start this off. Okay, we're going to figure out where does our parametric curve start and stop. Now, just knowing where it starts and stops, that's not enough. Because the question is, do you just draw a straight line? Is it linear? Is it something that does that kind of shape? Like how does the start and stop connect to each other? That's where we have to plot some points and see. So the start point and the end point are always going to be controlled by two things. One, the formula they give you, and two, the values you are allowed to plug into that formula. And we'll do an example in a minute where we just find the start point and the end point of that parametric curve on the right. So when you're finding a start point and an end point, there's four things you have to figure out. The x and the y value for the start, the x and the y value for the finish. Okay, so you need all four. This is going to control where it starts. So if you plug in what we're going to call T-min, one is going to be called T-max. If you plug in T-min into your x and your y formula, you will get this. So you plug in T-min into your x and to your y, and then you plug in T-max, which I'm representing by B. In the problem we're going to do in a minute, it's going to be a 1. You plug in T-max into your x, into your y, and that's your endpoint. So this is the start. That's the end. So let's try that on this one. Okay, so for T, what is my T-min? What's the lowest value that they're telling me I can plug in for T?
0.
0. So to find where this curve starts, you are going to plug 0 into both formulas. Now let's figure out where it's going to end. What's my T-max? What's the highest value they're telling me I can use for T?
The 1.
1. So you're going to plug in 1 for x and for y. Okay. What's the x value of my start point? Yeah.
Just 1.
Just 1? Yep. What's the y value for my start point?
2.
2? So this graph is going to start at the point 1, 2. And let's figure out where it's going to end. Okay. What's the x value where this graph ends? Negative 1. And what's the y value? 1. So this graph is going to start at 1, 2. And it's going to draw to negative 1, 1. So which way is it going to draw on the screen?
It's gonna go
From
quadrant to quadrant.
kind of like in terms of like left to right or right to left.
Oh, to the left. Oh, if we're starting at 1, 2, right?
Starting at 1, 2, and we're drawing to negative 1, 1. Which direction was that?
Right to left.
It's to the left. Every graph we've drawn on the screen this year has always been drawn left to right. If you think about it, when you hit graph, it always starts on the left edge and goes to the right. That's how the graph draws it as a function. That's not always true in parametric. It's going to draw right to left. And unless you're watching it as it draws it, if I put this graph on the screen, you can't tell me which one is the start and which one is the end just by looking at a picture. Okay? You'd have to actually watch it be done or figure out where it starts and ends. All right, let's try typing this in. So first thing is to type this in. You've got to go to mode, put it on parametric. Okay, once you put it on parametric, you can press y equals. And what's the formula I'm going to type in for my x values?
1 minus 2t.
So I'm going to do 1 minus 2t. And what's the formula I type in for my y's?
2 minus 2.
2 minus t. Now, there's a few things we have to do before we're ready to graph. What do you think I'm going to want to go into and set? Yep,
Your window.
my window. There's going to be a couple new options here. First thing is I need to tell the calculator what the domain for my parameter is, my min and my max. What's my t min and my t max?
0 and 1.
0 to 1. Now, the t step, that basically controls how many points the calculator is going to plot between the start and the end. For example, if you go by 0.1, the calculator will start at 0, it'll end at 1, and it's going to go up in increments of 0.1. So what's it going to plot for points? It's going to plug 0 into both, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, and 1. So by going in increments of 0.1, you will get 11 points on your graph. Is that good? Well, if it's a straight line, that's plenty of points. If it's a curve, depending on how big of a curve, 11 points might not be enough to see a smooth curve. You might need more. So if I go by, let's say, 0.01, what the calculator is going to do now is it's going to plug in every single number from 0 to 1, going in increments of 0.01. That's hundredths. That's 101 points between 0 and 1, counting by hundredths. 101 because of the including the endpoint on the 1. If you set the t-step too small, the calculator will start to freeze up. Like if you try to plot, let's say you set it to 0.00001. That's too many points. Okay, the calculator is going to get stuck. So I'll do that after and show you how you can fix it. All right, so now my graph is starting at 1, 2, and it's ending at -1, 1. What should my y max be? So the start and the end point are both on the screen. Yep.
3 and 0.
Yeah, we could do 3 for the y max, and what did you say for the y min?
0. Because like the
Yeah.
lowest is 1, so 1 plus 2 and 1 minus 1.
And what about the x max?
You could probably just do what it says, the 1 and to 1.
Let's do it like we did the y's.
All right, so
yeah,
that
we'll
would
do it
be-
the same way. Just have a little extra.
Yeah. -2, +2.
Yeah, I would say -2 and +2. That should be good. Okay, and if you put everything in, I think 0.01 is going to be slow enough that we should see it drawing right to left. Yep. And it just plotted 101 points to do what it did. Now, let me go to window and let me put in 0.001. Now it's going to plot 1,001 points. It's going to be 10 times slower than it just was before. So it's going to take 10 times as long to draw the graph now. I mean, it can still do it. I mean, it's going to finish in a reasonable amount of time. Maybe it took 15 seconds to do it. But I'm really plotting way too many points. For a straight line, you don't need 1,000 points, if that's what the calculator is doing. Now, let's just say you did 0.0001. Now it's going to be 10 times slower than it was before. That's not going to finish in a reasonable amount of time. You may not want to wait for that. So if you get something where it just is spinning and you want to stop it, just press second and press off and it'll stop spinning. Okay, now you can press window and you can fix it. Okay, another thing you want to be careful about with the t-step is it's nice to pick a number for t-step that if you count by the step, you land on the t-max. Okay, for example, if I count by 0.3s, the first point it's going to plug in for t is 0. And then what would be the next one? 0.3, and then 0.6, and then
1.2.
no, what's after 0.6?
0.9.
0.9, and then what would it try to do after 0.9? It would try to do 1.2, but it can't because that's bigger than what we said to go to. So the problem you're going to have is you're going to get a value at 0.9 and nothing between 0.9 and 1. So now, I don't know if you can tell, but that graph, that's not the full graph because your t-step didn't land on 1. And I can show you by fixing it.
Can you just do another like straight line up and down and show there's an intersect?
Okay, it's a little hard to tell, but I bet if I trace it, you can see it easier. Take this graph, and you'll see it's not the full, that is not the full graph. Well, you can just barely see it. I could exaggerate it a little more. If I do,
0.6.
Isn't
yeah,
there,
if we
yeah,
do like
isn't
a
there the intersect
0.6.
thing? Okay, yeah, wait, I see.
Now you can see it much better. I should have done that. So what's happening is you're missing part of the graph because you're getting a value at 0, you're getting a 0.6, and then the next one would be a 1.2, but it can't do it. So try, if you can, to pick a t-step that would land on your t-max. If it's off by like, 0.01 or something, I mean, that's okay. Like if you were doing this, like pi and 2 pi, that's going to come up a lot for t-max. And you're doing a step by 0.1, that's not bad. I mean, you're gonna get every number from 0, and you're gonna get 6, 6.1, 6.2, and then the next one would be 6.3. So you've got a little bit of a gap. So I mean, if you really wanted to, you could go by hundredths. Now you're gonna get 6.2. Okay. It just takes a little practice to get good at that. Any question on that? Okay, and the t-step becomes very important when you start to draw things that curve. Too few points, and your curve is going to look kind of jagged. All right, too many points, and it's going to take forever. So we got to kind of find a balance between graphing enough points and having it take too long. All right, so what we're going to look at here is how can you eliminate the parameter? What that means is to take something that's parametric and change it back to what we're used to. Okay, we could do that. We could do that with the last one. When you eliminate the parameter, what you're doing is you're going to be getting rid of the t, and you're going to be getting something in y equals format. Let's do the one we just did. What I need to do first, though, is I want to save a good copy of this graph. That's what it's supposed to look like. I'll just put that right there. Now I want to see if you have any ideas how I could eliminate t. This is going to be y equals mx plus b when I'm done. It's just going to be a line. It's going to have a y-intercept. It's going to have a slope to it. But I don't want to have a t. So anyone have a guess what we could do? Yeah?
like divide by t or?
You can't divide by t right yet because you need to get t alone.
Get t alone in which equation? It does make a difference which one we do.
I think the left one, because like it's more complex. Like usually when we're doing the simplifying thing, like I don't know how many minutes ago, we usually choose the more difficult one because then it's simpler to like trace it back and turn it back into the.
So how would you get t alone in that left equation? What would be your first step? Yep.
Subtract by 1.
Okay.
X minus 1.
So x minus 1 equals negative 2t.
Then divide by negative 2.
And then divide everything by negative 2. So that's gone. Now let's, we can kind of clean that up a little bit. We could write it as negative 1/2 x. Okay, that's x divided by negative 2. And what's negative 1 divided by negative 2?
That would be
0.5.
1/2.
Yeah, positive 1/2. Okay, well, that's the first step. So we got t by itself. Now what do you think we do? Yeah?
You can plug that in.
Yep. Plug that in for t. Right here. And that's how you eliminate the parameter. So we have y equals 2 minus, and now fill in what we just got for t. Negative 1/2 x plus 1/2. Let's put it in y equals mx plus b. So you're going to get negative 1/2. So it's 1/2 x. And what's 2 minus 1/2? 1.5 or 3/2. And if we just check quickly, does it look like the y-intercept of that line is 3/2?
Yes.
Yep. Well, let's put that in y1 then, and let's graph it and compare it to that one. So I'm going to switch back to function. I'm going to type this in. 0.5x plus 1.5. I want to set my window to be, your window carries over. So if you change your window in parametric, it will carry over to function. The equation does not, because there's no way for parametric to carry over to this. So what I typed in on the parametric screen, it's still there. I'm just in a different mode now. Hit graph. Okay, so that's the line that I got when I drew it as a function. Are they the same?
Yes.
One's continues onwards, the other one stops.
Right. And the parametric, it needs to stop. It cannot keep continuing like that if you want it to be exactly the same thing. The parametric one had a start and a stop. Well, this one needs to have a start and a stop as well. How can we figure out where this one should start and stop? We already did. When we graphed it parametrically, what was the leftmost edge of my graph? How far left did the line go? Yeah?
-2. -1.
Just the graph, not the window.
Oh.
-1. And what was the rightmost edge?
2.
2. So, no.
1.
1. So the leftmost edge is -1, and the rightmost edge is 1. Well, tell the calculator to draw that with what we just said. Okay, so now put that in parentheses. And then put the condition next to it. We want x to be greater than -1. And this goes back to what we talked about with like a piecewise function. Greater than or equal to -1. Now if you do that, well, it's better. You've got the left limit.
But it's array now.
What's that?
Now
it's like array, yeah.
Yeah.
Ignore the part on the x-axis. I can't fix that. That's as good as I can do. Now put the other condition next to it. What x value do we want it to stop at?
Pause.
So we want x, second math, less than or equal to positive 1. Now, it should look exactly like what we want.
You could put it into one equation for the.
Yeah, I don't know if you can do the conjunction. You can try it. Maybe it'll work. I've had problems with it in the past. That's why I did it as 2 separate ones. But that's how you change something from function to parametric. So let's go back to our answer. So now we have a function, but remember, your answer needs to be restricted. Okay? If you don't write down the restriction, you won't get it fully right. So the full answer is y equals 1/2 x plus 3/2, and x is greater than or equal to -1 and less than or equal to +1. That restriction needs to be there. And those two numbers come from the start and the end of your parametric curve. Just the x value. That's all you need. Okay, any question on that? All right, so let's try another one. Same directions, eliminate the parameter. You can eliminate the parameter without even looking at the 0 to 3. That's going to be important when we place the restriction on our curve. Okay, but let's just try to eliminate the parameter.
I think the only one we can do is the top one.
Yeah, so which equation do you always have to solve for t? You don't have a choice. You always have to do this one. X. You have to solve the x equation for t. So what does t equal from the top equation?
X minus 1. No, x plus 1.
X plus 1. And we're going to take that x plus 1 and then fill it in for t.
X squared plus 1.
And if they wanted that done out, what do you get?
X squared plus 1.
Wouldn't it be x plus 2x plus 1? No, x squared plus 2x plus 1.
X squared plus 2x plus 1. Okay, what shape is that if you were to draw it?
Parabola.
It's a parabola. But when you were drawing it parametrically, was there a restriction on t when we started the problem? Yeah, what's the restriction?
0 to 3.
That's the restriction parametrically. We need to convert that to a restriction as a function. So what we have to do is figure out our x values. Yep. So let's figure out the 2. If you plug in 0 for t, what do you get for an x value? -1. And if you plug in 3 for t, what do you get for an x value? 2. So that means this graph is going to be between -1 and +2. Okay. That's my restriction. Okay, let's draw it parametrically and just see. So I got t minus 1 and t squared. So t minus 1, t squared. Parameter is 0 to 3. We already figured out the x. It's -1 and 2. So let's do -2 to 3. Okay, just a little extra. Going 0 to 3, counting by 0.01, that's not bad. That's going to be 301 points. That's well within the calculator's, it's doable for a couple seconds. That's not bad. Now the y value, we're going to go, we got 0, 3 squared is 9. So I think -1 to 10 should cover us on the y. Perfect. So it is a parabola, but it's only part of a parabola. And it's the part of the parabola from -1 to +2. That's where the -1 and the 2 came from. Any question on that? Now, let's try point 1. Okay, let me kind of just take a snapshot of that. When I do point 1, would that improve the smoothness of the curve or decrease the smoothness?
Decrease.
Yeah, it wouldn't give me as good of a resolution. Now, to me, it still looks decent. Right? Maybe a little bit more blocky. I mean, it's hard to tell. Okay. Let's try going by.
0.5.
Let's do 0.2. Okay, I'm going slowly. Okay, still looks pretty good. Yeah, let's try 0.5. Okay, it's okay. Let's go by 1. Okay, now I can really see it. When you go by 1, you're getting a point at 0, 1, 2, 3. You're getting 4 points, and the calculator connects every point straight. So the more points you have, the smoother the curve will look. Any question on that? Yeah?
Is it different at all to how you wanted us to show you the window in the past?
Nope, say as long as you can see the whole graph on the screen. Just do a little bit of extra on the edges. Yep.
But
Now, what we just did is not always possible to do. There are some equations I could give you that you could not get t by itself. Okay, try getting t by itself in this equation. Good luck.
is it possible?
I don't think so. You can't, I mean, it's not a complicated equation. It's just the fact that you have a t as an exponent and a t as a term really messes you up from trying to get t alone. If you didn't have the t as an exponent, well, then you just subtract 3 and you're done. If you didn't have the t as a term, then you could use a logarithm to get the t out of the exponent. But you have both, and that's a problem. So it's not always possible to go from parametric to function. But it is always possible to go the other way. You can take anything and make it parametric. And a lot of times there's more than one way to do it. Okay? I'm going to give you what I call kind of a cheap way to do it. I mean, it works, and everything is correct about it, but it's just kind of a real cheap way to do it. So this is how you can take something and make it parametric, using these two equations. You just say, I'm going to let x equal t, and I'm going to let y equal my original problem that I had, just changing all the x's to t's. So it is a way to do it. Okay, so here's an example. If I said to write that parametrically, you could say, well, I'm going to let x equal t, and then I'm just going to change all my x's to t's in the other equation. That is exactly the same thing that I started with, except now it's parametric. And the way you can prove it is change it back. Which equation are you supposed to always solve for t? X. Well, it already is. X is solved for t is by itself. Just like we did right here. Take what t is equal to and plug it back in for t in the other equation. What does this say t is equal to? X. So plug that in for t in the other equation, and what would you get on the right-hand side?
3x plus b, 3x plus 1.
3x plus 1. That's exactly what we started with. So it works. It's just kind of a cheap way to take something that's not parametric and make it parametric. And there's probably other ways you could figure out how to do it as well, but that's the simplest. Okay, let's try it on this one. So they want us to write this quadratic equation parametrically. What could I let x equal?
T.
Just let x equal t. And then what would y equal?
3t to the fourth plus 7t to the third minus 8t squared plus 2.
Yep. And technically, that is a parametric system of equations. Doesn't really make a lot of sense to do that in that particular problem, but you can. Okay. Any question on that one? Okay. All right, so let's find the equation of a circle, specifically at the origin. Well, to find the equation of a circle, it really starts by just figuring out how do you represent a single point on a circle. Because if you can represent a point, then you can represent millions of points. There you go, there's your circle. So let's think about how you would describe one single point on a circle. Remember, it has to be in terms of an x formula and a y formula. So here's a point. What do you think I could draw here that would help me to see this? Yeah?
Triangle.
Yeah, I'm going to make a triangle. This is your x, this is your y. So I need a formula that's going to calculate the base of the triangle and a formula that's going to calculate the height. Now, what's changing inside this triangle as you drag this point around the circle? Besides the x and the y, we're going to come up with a formula for those. But something else is changing inside the triangle. Yeah?
The angles
Yes.
for those triangles.
This angle right here is changing.
It stays 90 degrees at the point between x and y,
Yeah.
but another two are changing.
Right. The other two will change. And we usually use as our reference angle the angle between the hypotenuse and the x-axis. So that's the angle we're going to reference. Now, what do we normally use to represent an angle that we don't know?
Greek letter.
We use what?
Theta.
Yeah, we use a Greek letter. Well, we're going to do this parametrically. You can't use a Greek letter. It's not going to make sense. What letter do we always have to use to represent an unknown when we're doing parametric? Yeah.
I was thinking what Jacob said, like theta. If we can't use alpha, beta, gamma, we have to use theta.
Hold on. T. So what's going to be changing this time is t. T represents whatever is changing. And in this case, it's the angle between the hypotenuse and the x-axis. Okay. So what would be a formula that would calculate x? Yep. Well, t isn't a side, t is an angle. So you got to come up with a formula to calculate x based on this value. And we don't know what this is. We could just call this side r. Like it's like our radius. But I think, let's just, to make it simple, let's do a unit circle. Yeah? Okay, so what would be your formula for x?
Would be y over x or equals
Square root of 2 root 2.
Yep.
The tangent of 2 is the y over x.
Well, we want a formula for just x by itself. So we want a formula doesn't involve y and x in the same trig function. We want separate trig functions. Yeah?
Law of sines, law of cosines.
Nope, it's a right triangle. So you're gonna stick with right triangle stuff.
Oh, y squared minus 1 squared, or like a squared plus b squared equals c squared, so therefore c squared minus b squared equals a squared.
But you're solving for an angle, so you need to use a trig function. You can't use Pythagorean theorem to find an
But
angle.
then, wait, are you saying x is an angle or x is a side?
X is a side.
Is it y over t?
That's x, that's y. So what's the trig function that would involve x and the hypotenuse?
Cosine.
Cosine. All right, so what would that be? Cosine of x, or cosine of t equals what?
X over 1.
So then, if we want to solve that for x, what's x?
Cosine t.
Cosine t. What do you think your formula for y is?
Cosine t equals, not cosine, sine equals y over 1.
So y would just equal sine t. That's the equation of a circle, specifically a unit circle. Parametrically. X is cosine t, y is sine t. All right, let me just put that in and show you what it looks like. Now, what did I just say the radius was?
1.
Yeah. T. All right, we could do, let's try zoom square, because we want this to look like a circle, and the screen is not a square. It's wider than it is tall. So if you do zoom 5, it should look, actually let me recenter it by doing zoom 6. There we go. Now, if I do zoom 5, looks circular, maybe you can't see it, but if I zoom in now, perfect. Nice circle. Now, you have to know what your T max and T min should be. In order to get a full circle, what do you have to start at for T min and end at T max?
Same place.
You have to start and end at the same place, radian-wise. And how many radians do you have to go through to get a full circle?
2 pi.
You have to go through 2 pi. If you set your window from like 0 to 3, well, 2 pi is 6.28. You don't get a whole circle. Okay, so to get a full circle, when you're doing a parametric graph with sine or cosine, you've got to go to 2 pi. And what's going to happen if I step in increments of pi over 2?
It's going to be like a sharp, it's going to turn into like a square.
Yeah, because you're going to get 0, 90, 180, 270, 360. You're going to get 5 points. It's going to look more like a diamond.
Yeah.
Okay? It should be a circle, but you didn't plot enough points to see a circle. So I would say when you got to go to 6.28, if you step in increments of 100th, well, that's way too much. If you step in increments of 1/10, that's good.
So if you did pi over 4, it would like an octagon?
Yeah, because you get increments at 0, 45, 90. Yeah. You would, I mean, you'd get an octagon. That's not what we're supposed to get, but that is what it would look like. Oh, don't change your T max. Change your T step. Now I did do pi over 8, but it's hard to see because the circle is so
Well,
small.
why wouldn't it pi over 4 be? Because
Is it?
pi over 2 is,
Oh yeah. I did a 16-sided.
yeah.
That's a 16-sided shape. So yeah, if you did pi over 4, that's actually what I meant to do.
Yeah.
You'll probably see the octagon, even though it's pretty small. You can see it. The bigger the circle, the easier it is to see.
So for if you made your t min above 2 pi, would the calculator like overlap itself? Maybe screwed up.
You mean the T-max?
That's what I mean.
Yes, it'll start to overlap. Yeah, so if you went to like 4 pi, what's going to happen now is it's going to go around more than once. You can't see it,
Yeah.
but it did. Now, if I step by an amount that's not a nice number that ends on my T-max, like 0.5, it's going to go around more than once. And now, could you see it? It got bolder because each point was a little off from where it was the first time. That will happen if you don't step by an amount that's divisible into the T-max. Yeah. Might even be easier to see if I made it like 0.3. Well, I don't think that was easier to see actually, but yeah. So. All right, any question on that? So, let's find the equation of a circle with the center at the origin and a radius of 2. Now remember, when we did this, what was our radius in this problem? 1. How would you bring this 1 to the other side if it wasn't 1?
Multiply.
You multiply by it, and it would be in front. So really, it's like there's a 1 there. So what do you think the formula for a circle with a radius of 2 is?
2.
2 cosine t.
Cosine t and
2 sine t.
2 sine t. So if you type that in, 2 and 2. Change your t step so it looks nice and smooth. There you go. Circle. You can see it tracing over itself that time. You could tell. Because I forgot to change it back to 0 to 2 pi. Now, you got to think a little bit differently for this part. What if I wanted to translate that right? 1 unit. What would I do? Yeah?
Either t plus 1. You said right. Right?
Mm-hmm.
Right.
This
So
is not what we're used to.
t minus 1 or the entire thing minus 1. Because usually, like I know you said it's not what we're used to, but like conventionally for like other equations is usually adding something
So if you
on
wanted
the inside or outside that moves it.
So if you wanted to shift it to the right one, you would do a plus 1 into the x formula. If you wanted to shift it left 1, you could do a minus 1. The transformations are actually simpler because you're breaking it into 2 separate formulas. You don't have to do the opposite with anything. You want to go left 1, minus 1. Right 1, plus 1. If you want to move that up, you could do a plus 1. But you do it to the y formula instead of the x. Add 1 to all the y's.
Is there ways to make it more narrow or wide?
Yep, we could make it an oval if we didn't do the same number for both x and y. So if one of them was like a 2 and one of them was a 3, now this should look more,
Ovular.
yep, it'll look more elliptical. It'll have a radius of 3 on one axis and a radius of 2 on the other. Yep. So when we did this circle problem, in order to see the whole circle on the screen, you've got to have your x min and max go from -2 to 2. But what did the parameter have to go from to get one full circle without tracing over itself?
Could you repeat that?
To get, what do you have to set for your parameter so you get one circle and it doesn't trace over itself?
0 to 2 pi?
You got to go 0 to 2 pi. So there's a difference between the window and the domain for t. Okay. The window is so you can see it. The domain for the parameter is how much sketching it does on the screen. Okay, and then the last one, we just have a few different graphs we're going to look at and see if we can get pictures for on the screen. So they're going to involve sine and cosine. So it takes a little practice to kind of get used to, our window. So we're going to find some complete graphs. Okay, so here's our first one. To figure out what your window needs to be, you need to break down what you're looking at. You have a t times cosine t. We know that no matter what you fill in for t, the cosine of t is always between what two numbers? What's cosine of anything always between?
0 and 1.
Negative 1 and 1. So this part of the formula is between negative 1 and 1. What's t going to go between? Zero and 4 pi. So if everything lined up just right as you were filling things in, what's the most negative value you could get from that expression?
0.
Well, you can go smaller than 0 there.
Negative 1.
Smaller than that.
Oh, negative 4 pi.
Negative 4 pi. If everything lined up just right, if this was a negative 1, at the same time this was 4 pi, you could get a negative 4 pi for your x. What's the biggest value you could ever get for x?
4 pi.
Yep. So negative 4 pi to 4 pi is the biggest and smallest you could ever get for x. Now, do the kind of the same reasoning for y. What is sine always between?
0 and 1. The same, negative 1 and 1.
Negative 1 and 1. And t is still between 0 and 4 pi. So what's the smallest and largest y value you could get?
Isn't it the same?
It's the same thing. Yep. So we could hit negative 4 pi and positive 4 pi. Now, to get a full picture, we need to go from what to what for my parameter. Because we're dealing with sine and cosine. Yep.
0 and 2 pi to have
Zero.
full
Yep.
cycle.
And I would go by 0.1s. And that's going to draw about 60, well, 0 to 62. I think it's about 62 or 63 points. So enough. Okay, let's type it in. So we got t cosine t, t sine t. Notice I didn't have to change much there from the equation of a circle. What do you think this one's going to look like? Anyone have a guess? The radius is a variable. What would happen if you took a circle and made the radius change? What shape do you get?
I don't think it would be a circle anymore. It would be something that's continuously changing, like a spiral.
It would be a spiral. And because we're going 0 to 2 pi, we're going to get exactly 1 revolution of the spiral. If you wanted to see another revolution, this graph doesn't end where it started. So if you increase your t max, let's go 0 to 4 pi, you will get more of a picture. Now you're going to get 2 revolutions of your spiral. And I think that's what they wanted me to do, 0 to 4 pi. So that one's a spiral. Any question on that? So I did 4 pi because that's what they told me to do. I wanted to show it to you with 2 pi first. So you saw 1 revolution of the spiral, and then 4 pi gives you another revolution.
So you just change the mode of the calculator to the conjugate thing, and then you put it in, you get the spiral from it?
You set it to parametric.
Yeah, parametric.
Yeah. All right, let's try this one. So this one is 5 sine t for x and 5t cosine t for y. Okay, let's start with this. Sine is always between what 2 numbers? Yep,
Negative 1 and 1.
negative 1 and 1. If you multiply something that's between negative and 1 by 5, what will your new value be between?
-5 and 5.
Yes. So for x's, we only need to worry about negative 5 to 5. Now let's look at the y's. What's cosine t always between? Negative 1 to 1. Oops. My ampersand ability went out the window. Negative 1 and 1. And now think about this part. 5t. What's the biggest that this part could ever be? 5 times 20.5. That's the biggest.
102.5.
Yeah, say you could do 103. I mean, I'm not worried about doing 102.5. Let's just do 103.
The smallest point would be the opposite of it, which is going to be the negative 103.
No, just
Could
goes
5t
from
be
zero.
negative 103?
No, just 0.
Could just be 0, because that's as small as t goes. So now, if you take a number between 0 and 103 and multiply it by something between negative 1 and 1, what is the biggest result you would ever get? You can't go bigger than 103. So on our y-max, let's go 103. And now, if you take something between 0 and 103 and multiply it by something between negative 1 and 1, what's the most negative result you could get?
100. Negative 103.
You could get negative 103. Okay, so I think we got everything lined up. I'll put in your Tmax. It's supposed to be 20.5. Does it start at 0? Yep. Going by 0.1s, I'm not sure that's going to be enough. Let's try 0.1 and we'll see how it looks. So we got 5 sine t. And we've got 5t cosine t. 5t cosine t. Well, I guess 0.1 was okay. You get the gist of what it looks like. Yeah. It's kind of like watermelon, I don't know, something like that. I could have gone a little bit more. Maybe I should have done like 110, negative 110, but I am getting it on the screen. Okay. So what's happening here is this y value increases and decreases without bound. The bigger you make t, the more and more and more and more the y value is just going to keep going. On the x, that's not true. You could let t be 1,000,000, and you'd still get an answer between negative 5 and 5 for x. So y increases and decreases without bound. X is pinned between negative 5 and 5. So if you make Tmax higher, you'll get more stripes kind of in the watermelon. More and more and more. Any question on that? Okay, and there's one last shape, which I'm just going to type one in and show you, that if it has this exact format, let's pick a number for A. Let's do 5t minus sine t. And let's do, it has to be the same number, 5 times 1 minus cosine t. This particular shape has a name, and it is called a cycloid. It's called a cycloid. Let me hit graph. Oh, I didn't adjust my window. Let's do zoom 6, start with that. Not a great picture. Let's set our x max a lot higher. Okay, well, that's one. If I set my T max higher, like let's say I set it to 20, it keeps going. Okay, this shape, that's called a cycloid. And depending on how high you set the T max, it just keeps going. Now, interesting thing about a cycloid. If you take that graph and you spin it, let's pretend that's upside down. Let's say that you had a platform up here, and you had another platform down here, and you were looking to build a track that something was going to go down on, maybe like a roller coaster, and you wanted it to go as fast as possible. Like, should you just build a straight line and just have it go down like that? Well, it turns out that that curve right there is the best possible curve if you want to get something from this level to that level in the fastest amount of time. Okay? It's the curve of part of a cycloid. And that is called, which I already showed you, it's called the curve of quickest descent. So you don't even really have to write it all down, just as long as you understand that to get from here to here in the fastest way possible, it's the curve of a cycloid. Well, flipped over. We don't really do a lot with cycloids. It's just if you see that pattern where you have a t minus sine t and a 1 minus cosine t, these two numbers have to be the same. They both have to be 5 or 6 or 7. It can be whatever number you want. But if they're not the same, it's not a cycloid. I don't remember what happens if you change one and not the other. I don't know. It still looks kind of like a cycloid to me, but they don't call that a cycloid anymore. The two numbers have to be the same. So the best way to figure out what some of these parametric graphs look like is just to play with it. Okay, what if I make the 5 a 2? What if I make the 7 a 3? Like, how does it change it? Because I'm not as familiar with these either, so a lot of times I just play with it and see what happens. All right. So that's parametric equations. I can make this.
What? I was just gonna erase that whole thing.
The whole thing? No. So the homework 1 through 17 odd,
Just the bottom.
and then 21, 22, 25, 26, and 29 to 33. A lot of graphing. You might just have to copy down the sketch onto the paper. That's fine. Take a look at that tomorrow.